Welcome to this presentation. Completely different topic, leak testing. And I give you my introduction in a second. If you look on this picture, a few of you may think, hey man, this is the wrong event. This is the refrigeration air conditioning trade show, not automotive. No worries. You're absolutely correct. And in a minute, we are going to talk about one specific case, how to automate leak test procedure in refrigeration air conditioning application. But I choose this picture because from my perspective, my personal impression, automotive is one of the most automated industries. Everything is automated, production processes, test measurements, process control, almost everything. And I think that this is not the case in refrigeration air conditioning. And yeah, welcome to this presentation about efficient leak test, robotic leak test by the example of refrigerators. And in these presentations, I'm going to give you some insights about what are the challenges of leak testing in refrigeration and air conditioning industries, and what exactly are the challenges to do automated leak tests. So just to get into it, let's have a short look about what are the reasons for automation. And it's pretty simple because it's all about efficiency. Yeah, saving time, saving money, increased quality, increased profitability in the end. And especially for the last few years, everybody is talking about Industry 4.0. So there is a high need to have a seamless data recording. Everything needs to be recorded and saved. Each process parameter, each test measurement needs to be saved and stored together with the individual product. And to do this, you need to automate your processes. And now let's have a short look about how leak test processes are automated in other industries than refrigeration and air conditioning. I promise this is the last slide look into other industries than refrigeration and air conditioning. There are a bunch of different test methods for leak testing. You can start with pressure decay or flow methods where you simply fill your test object with pressurized air and you monitor over a certain period of time if you have a pressure drop caused by leaks, due to leaks. And then you have so-called tracer gas methods. So you fill your test subject with a tracer gas. Helium, for example, is a well-known common tracer gas. You put it into a chamber and you collect the escaping tracer gas in this chamber. And if you do this in an atmospheric test chamber, it's the so-called accumulation test. To reach the highest sensitivity and shortest cycle time, you can also test your product in a huge, massive vacuum chamber. And there's a so-called sniffer test to locate leaks, which you can also easily automate by simply adapt your sniffer line to a robot. Okay, now let's move over to refrigeration air conditioning industry. And if we are looking to test single components like compressors, valves, fittings, pipes, and so on, then you can easily use the same mentioned test methods. You can put it in a chamber, you can use tracer gas depending on your specification. But this is not the case, or it's not that easy if you are looking about final products of refrigeration air conditioning industry. Let's think about fridges or AC system heat pumps. And why is that? What are the challenges to leak test final products in the heating, ventilation, air conditioning industry automated? Number one, it's the dimension and the complex geometry. And you see it in the picture. You have a complex scenario of pipes which requires high volume, that volume. And if you like to test such a huge test object in a chamber, you have to design a huge test chamber. Huge test chamber means huge price, high price, and long cycle times, test times. Next reason is the final product is often equipped with isolation materials and foams. And you will get in trouble if you put such a product in a vacuum chamber, because a foam is a material with high porosity. So you will get trouble to reach your required vacuum because you have a lot of outgassing effects. Next one, we have very tough leak specifications. So in refrigeration, air conditioning, we are looking for very, very small leaks, which are pretty close to the physical detection limits of many test methods. We also have large production tolerances, especially if you see these pipes. There's also a production tolerance. Even if you have exactly the same product, it may look different from product to the next one to the next one. And we have typically a high number of product variances. And this is the reason why manual sniffing, tracer gas sniffing, is still state-of-the-art test method. Now you may think, wait a minute, sniffing seems to be a suitable test method, and a few slides before, you told me that you can simply adapt a sniffer line to a robot and then you have an automation, right? But this is not the case. Let's have a look into some details. We have very tough leak specifications. So in refrigeration, air conditioning, we are typically looking for leaks which are 3 gram per year down to 0.5 gram per year refrigerant loss, which is almost nothing. But we still need to have a solution which is capable to find such small leaks. These leak rates are pretty close to the physical detection limit of sniffing methods. So you need to test very carefully and consider that there is something like a practical detection limit and a theoretical detection limit. When you have this theoretical detection limit, which is given, there's some issue with the slides. While you have the theoretical detection limit, which is given by the sensitivity and the resolution of your leak detector, you have the practical detection limit, which takes in consideration that you have a worker who impacts your measurement. Does he have a good mood? Is he working carefully enough? And so on. You know what I mean? So, and the most important recommendation is therefore to find these small leaks, stay as close as possible with the sniffer line to your potential leak spots. If you have a pipe, a leak will form kind of a cloud, and the smaller the leak, of course, the smaller the cloud. And if your distance to the sniffer line is too big, then you will not catch the leak. So, distance matters a lot. Okay, if we now look to a typical application, there's this so-called engine compartment of a fridge, where you have the backside of a fridge, where you have all these joints which needs to be tested, and all these joints are handmade. So you have huge production tolerances. Let's have a look. Our learning so far, the recommendation is stay close to the leak, stay close to these joints to catch the smallest leaks. But we also know we have huge production tolerances. Even if you have the same type of fridge, it may look different. The position of these joints may differ by a few centimeters easily. So the question is how to automate such a sniffer leak test if the position of the joints will differ by a few centimeters, because you cannot simply take a robot, program certain positions while the real position of the leak will differ. And the idea is to stay close to the leak, integrate a precise, intelligent 3D camera system, which is, before you do the leak test, detecting the true position of the leak. So the camera system will do something like this. It creates a three-dimensional image, a cloud of dots, of many dots, thousands of dots, millions of dots. And of course, to process this image will take a lot of computer power. And so you have to decide for certain search areas. So you define search boxes. These are the blue areas where you expect, even due to production tolerance, where you expect the joint to be. And the camera system is then creating images like this. Here you have the dryer on this side. Yeah. Does a robot path planning and hand over the information to the robot so that the robot is able to position the sniffer tip right in front of the leak or in front of the joints. Okay, now it seems we have a solution to automate this system. We have a solution to position a sniffer tip in front of the joint. But as I told you, distance matters, and distance matters a lot. And what you see here is a cut image through a pipe showing three different scenarios. Scenario number one is the leak is faced 0 degrees. It's placed directly in direction of the sniffer tip. Scenario number two is the leak is facing 90 degrees away from the sniffer tip. Scenario number three, the leak is facing 100 degrees. It's on the opposite side of your sniffer tip. And we did some measurements. Even if you have a system which is able to position the sniffer tip right in front of the joint, these scenarios can happen. And the test results you see here, with a leak of 0.33 gram per year, you will almost see nothing if the leak is not facing to the sniffer tip. So what's the recommendation here? For a worker, the recommendation clearly is try to circle around the joint with the sniffer tip. A worker can easily do it. I have some doubts if a worker finally will do it, but he can. But this is somehow tricky to solve with a robot. So how to cope with this challenge? And the idea is use a kind of customized sniffer tip. And in this case, it's a brush tip. And what's happening inside this brush tip, you can see in this cut image right here. It's kind of shielding the joint so that the sniffer can easily catch the gas which is escaping through the leak, even if it's on the backside, because you have cover around your joint. And with that solution, with that solution, we found out, hey, it doesn't really matter where the position of the leak is. If it's 0 degree, 90 or 180 degree, the measurements are almost the same, and in each case, you will catch the leak. So the solution, how to get this sniffer leak test automated, simply is just combine your leak detector with a robot, with an intelligent camera system, and customized sniffer tip, and you will end up with a solution similar to this one, which can detect fully automatically your products. And just to give you an example how it works, this is the real life view of your compartment. The camera system will create a 3D image, do the robot path planning, and the robot is then testing all the joints. And at the end of my presentation, I got a video, real life video, and you have to watch carefully, because when I saw this video the first time, I was thinking, hey man, this is something like a speed ramp. This is fast forward or something, but it's real time. And just have a look. Fridge is coming. This is the scanning process for the camera. Now the robot starts. 1, 2, 3, 4, 5.
Wheels, the car.
6.
In.
Job done. Yeah. And I have some doubts if an operator can do the job in the same speed with the same, let's say, accuracy. So, yeah, that's the solution. And yeah, if you like to learn more, you're welcome to visit our booth. It's right next. It's just a few steps. You can't miss it. Inficon over there. We have such a system on our booth. You're welcome to visit us for any questions. In case of any question, because we have no moderator, no microphone, I would recommend I will stay here for a while and yeah, just come back to me in case of any questions. Thank you.